Here we'll do a quick example where we identify the sample and the population in a survey. The question asks, a survey asked 2,000 U.S. households if they currently own at least one pet. The results show that 69% of households do own at least one pet. Identify the sample and the population in this situation. Remember, with a survey like this, the population is the group that we're interested in knowing something about. But it's usually not feasible to study the entire population, so we gather data from a small subset of that group. So, in this case, we're interested in knowing about all U.S. households, so that's the population. Notice that that wasn't explicitly stated, but it's clear from the problem statement that that's what we're interested in knowing about. Because it's infeasible to study all households in the U.S., we take this sample of 2,000 households. We gather data from them, and we use that to draw inferences about the entire population. Here we're looking at the idea of representative samples. So if we're looking to measure something about a population, we want to gather a sample to measure, and we want to make sure that when we do that, the sample represents the population, that it looks similar to the population as a whole. So we'll look at a couple examples here. First of all, to find the average annual income of all adults in the United States, suppose we sampled representatives in the Congress of the United States. It turns out this is not a very representative sample. First of all, the salary for representatives in Congress is set at a fixed number. And that number is relatively high compared to the average income for all adults in the United States. So it's not representative, because if you look at the whole population, there are some people who make very little and some people who make a lot. And in the Congress, there's a fixed value that's unlikely to be similar to the average value of all adults in the US. So it's not a very good representative sample. We would say, no, this is not representative. The second example says to find out the most popular cereal among children under the age of 10, you could stand outside a large supermarket one day and poll every 20th child under the age of 10 who enters the supermarket. It's not clear that there's any bias in this one. This seems like a pretty good way to find an answer to this question. If you poll children coming into a supermarket of the right age group, you're likely to get a pretty representative sample for all children that do this. Now, you may want to pick different areas of the country, for instance. There could be differences depending on where you look, but without going any deeper, it doesn't look like there are any obvious red flags that this would not be representative for all the answers you're looking for. So this one looks fairly good. And the lesson from these is just that when you're gathering a sample, it's important to look for a representative one that's likely to look similar to your population. You don't want a sample that's chosen too narrowly or that's chosen with some sort of obvious bias. This is a simple example that illustrates a way that a sample can be biased. Here, a coach is interested in how many cartwheels the average college freshman can do at his university. 8 volunteers from the freshman class step forward. After observing their performance, the coach concludes that college freshmen can do an average of 16 cartwheels in a row without stopping. Is this sample random and representative? In general, a good sample is random and representative. A simple rule of thumb for deciding whether a sample is random or not is just to think about whether or not every member of the population is equally likely to be selected. If so, there's randomness involved. To decide whether or not the sample is representative, think about whether the sample looks similar to the population. Here, the biggest source of bias that we observe, and bias means that the results will be skewed, is this voluntary response bias. Voluntary response bias means that rather than picking people to ask, the coach asks for volunteers. In this case, people that are able to do more cartwheels are more likely to step forward and volunteer for the study. Because of that, we conclude that this probably isn't a very good sample to do this study. A voluntary response bias also comes into play in surveys that have questions where certain responses are more favorable than others. In this example, we're going to decide which type of sampling is being used in each description. In the first situation, we have a soccer coach who selects 6 players from a group of boys aged 8 to 10, then 7 players from the group of boys aged 11 to 12, and finally 3 players from a group of boys aged 13 to 14 to form a rec team. Notice the key here, which is that the coach has divided the group into segments based on their ages. So there's a segment from 8 to 10, a segment from 11 to 12, and then a segment from 13 to 14. And from each segment, the coach has selected several players. So after dividing into segments, the sampling could be either stratified or clustered depending on what happens next. But the fact that we're choosing a couple from each group makes it stratified. If we chose a couple of groups all together, that would look more like cluster sampling. So this first one is stratified sampling. Now generally with stratified sampling, we select the same number from each group. In this case, the coach didn't do that. He selected 6 from one group, 7 from another, and 3 from another. But generally speaking, with stratified sampling, we select the same number from each group. In the second part, there's a pollster who interviews all human resource personnel in 5 different high-tech companies. And this may be hard to see at first, but the fact that this pollster selected 5 companies leads you to think that they looked at all of the companies that were out there and thought of each company as a group, and they selected all human resource personnel from a few of these groups. So by dividing them into groups, again, we can think about either stratified or cluster sampling starting that way. And then because the pollster selected everyone from a couple of groups, that's cluster sampling. If they had selected a few from all the groups, that would be stratified sampling. But the fact that they selected a few full groups makes it cluster sampling. The third one, a high school educational counselor interviews 50 female teachers and 50 male teachers. Notice again that there's a separation of categories, and so the teachers have been separated into male teachers and female teachers. They've been divided into groups, and then from those groups, some have been selected, an equal number from each, which again looks like stratified sampling. Next, a medical researcher interviews every 3rd cancer patient from a list of cancer patients at a local hospital. And the key here is that term every 3rd, which is what identifies this as systematic sampling. Systematic sampling is where we have a list like this, and we pick some step like this, like 3, and we check every 3rd, or we could pick every 5th or every 10th. Whatever it is, that systematic moving through the list is what makes this systematic sampling. The next one, a high school counselor uses a computer to generate 50 random numbers and then pick students whose names correspond to the numbers. Notice how there's no division into groups, there's no systematic process. This is the full population of students, and we just select random numbers from that full group. And that's what makes this simple random sampling. That's kind of the simplest version, where we're looking at the full population and using a random number generator to just select without any division into groups or anything else. Lastly, a student interviews classmates in his algebra class to determine how many pairs of jeans a student at his school owns on the average. Notice here that this student is looking for information about the whole school, but rather than looking at a full student list and selecting randomly from them, or selecting every 3rd student, or even dividing them into groups, the student just asks the students nearby, the students that are in his class, next to him, which makes this a convenient sample. In this example, we'll see how to select a simple random sample from a population. The population we're given is a set of 6 quiz scores, and there are 10 students. In this example, we'll draw a dot plot, and we're given data that represents the ages of 30 randomly chosen NBA players. And the first thing we need to do is draw an axis that will cover the full range of the data. So just kind of scanning through, it looks like the lowest value here is around 20, and the highest value is about 36. So let's make sure our range will at least cover those values. Let's draw an axis here with values from 20 up to 36. Now that we have our axis, all we need to do is read through each of these data points and put a dot for each one. So for the first value at 22, we just put a dot above the 22. Then we have 28, so we'll put a dot at the 28. Notice it hovers a little bit above the marker, but it doesn't really matter how high we put them as long as we place them at consistent heights, just so we can visualize the final result. That'll make more sense as we draw more of these. The next value is at 20, then at 24, then at 26, then 21, 27, and then we get another 28. So this is the second time we've seen 28. So we won't draw the second dot at the same place as the first one, but we'll put it right above it. So now there's a second dot at 28. Then we go to 31 and 29 and just continue on entering these. We hit another 24 here, and again we just put this one above the first one at that location. Then we have another 22, another 21, then a 25, another 22, another 25, 30, another 29, another 20, and so on. There's our 36, another 24, the first 23, another 36, another 24, another 29, and we'll just finish this out. So there we see our dot plot, where each time we run into a value we've already drawn a dot for, we just draw a one a little bit higher. So notice that the height of these stacks tells us how frequent an age is. So the more frequent ones are over here, and then the 36s, there's kind of what we would call an outlier. They're far out from the other data points. And for instance, 30 is relatively rare. There's only one of those, and so on. So there's a lot we can tell from this plot, and we'll draw other types of plots later on that fit this same kind of pattern of looking for where the data is clustered and where it's spread out. But a dot plot is a very simple way to observe that at first.
Here we're going to build a simple frequency table. The problem states that 19 people were asked how many miles to the nearest mile they commute to work each day, and their responses were recorded in this data set. The frequency table lists each possible data value and the number of times that data value occurs. So we put two columns like this, one for the data values and one for their frequencies. Now we'll go through the data set, and for each unique data value that we see, we'll list that in the left-hand column. Once we've filled in all these data values, now we just need to count how many times they occur. So, for instance, I noticed that 2 appears twice in the data set, so it has a frequency of 2. 3 appears only once, so it has a frequency of 1, and so on, and I fill in the rest of the table. And it's really as simple as that. Once we've filled in the frequency table, a quick check that we can do is add up all the frequencies, and they should add up to how many data points we have. And here, if we add up these frequencies, we do find a total of 19.
In this example, we'll build a frequency table for categorical data. We're given a sample of NBA players with their position, which is a categorical variable. It divides them into categories: point guards, shooting guards, small forwards, power forwards, and centers. And we're going to build a frequency table to go along with this. So the categories will be the divisions, and then we'll count the frequency in each category. So our frequency table will start with 2 columns, one for the position and one for the frequency. And then we'll add a third column for relative frequency. It's a good thing to include when you draw a frequency table. It's not entirely necessary every time, but it's a good idea to include it when you can. So the positions, we have point guard, shooting guard, small forward, power forward, and center as our 5 categories. And then we just go through and count how many there are of each one. So for point guards, for instance, we have 1, 2, 3, 4 of them. So the frequency is 4. For shooting guards, you can count 1, 2, 3, 4, 5, 6, 7, 8, 9. For small forwards, we have 1, 2, 3, 4, 5, 6, 7. For power forwards, we have 1, 2, 3, 4, and 5. And then for centers, we have 1, 2, 3, 4, and 5. And notice that if we add up those frequencies, we should get the total number that we have, which is 30. So we should get 30 if we add those up, and you can check that by adding those frequencies. For the relative frequency, we need to divide each frequency by the total number that we have in our sample, which is, again, 30. So for the relative frequency of point guards, we would divide 4 by 30. which we could write as a fraction, or if we wanted to, we could write that as a decimal, which comes out to about 0.133 or 13.3%. Then for the next one, we would divide 9 by 30, which works out to 30%. 7 out of 30 is 23.3%. And then 5 out of 30 is about 16.7%. And that's for both of the last two categories. So again, a frequency table is pretty easy to construct. All you have to do is count how many fall into each category. And in this case, the categories were the positions of the players. Here we're going to build a grouped frequency table using the data set of NBA players with their points per game shown below. So we have 30 values ranging from 1.4 up to about 24. And we're told to use a class width of 5 for our grouped frequency table. So we want to start low enough that we can cover all of them. And rather than starting at 1, let's start at 0 just to get a nice round number and make it easy for ourselves. So in our frequency table, the first column will be points per game. And our first category, the first class, will start at 0. And we'll go up to 5. But remember, we won't go all the way to 5 because we don't want to overlap our classes. So the first one's going to go up to just less than 5. Let's use 4.9 to represent just less than 5. And then the next one will start at 5.0 and go up to 10, but just below 10, so we'll stop at 9.9. And then we'll go from 10 to 14.9, 15 to 19.9, and 20 to 24.9. We don't need any more classes because that's as high as we need to go to cover everyone in this data set. So the next column will be the frequency, and then lastly we'll have the relative frequency. Since there are 30 values here in our data set, once we have the frequencies, we'll just divide each one by 30 to get the relative frequency. We won't show this in detail for all of these classes, but just for the first class, from 0 to 4.9, we'll go through and select all the ones that fit into that category. So between 0.0 and 4.9, in the first row, we find 4.9. In the second row, we find 1.4 and 2.0. And in the third row, we find 3.0, 4.3, and that looks like all of them. So there are a total of 5 that fall into that range. And then we can continue this on for all the others, but I won't show the counting. You can go through and do that yourself, and I'll show you the results here. So once you count all the others, you should get 11 for the second class, 5 for the third class, 4, and then 5 for the final class. And then if we divide each of these by 30 to get the relative frequency, 5 divided by 30 is 0.16 repeating, so you can round that to 0.167 or 16.7%. And then 11 out of 30, we could round to 36.7%. 5 out of 30 again is 16.7%. And then 4 out of 30, we could round to 13.3% to get the relative frequency for each. So it's really just counting. The only thing to keep track of for grouped frequency tables is to make sure your classes are all evenly wide and that none of them overlap. That's the important piece. Here we'll build a histogram using the data set for the players in the NBA with their points per game listed here. In the last example, we built a grouped frequency table, and now we're going to build a histogram that matches it. So we're going to take the frequency table we built earlier and just draw this histogram to represent the same picture. So to do that, we'll start with a grid, and the x values will range from 0 up to 24.9 or up to 25. So we'll have 0 here, 5, 10, 15, 20, and 25. And each of these classes will fit between two of those values. So the first class goes between 0 and 5, the next one goes between 5 and 10, and so on. And of course we know that it goes just up to 5, but not including 5, and so on. But we'll draw it as if it goes all the way to 5, just to make the picture as simple as possible. Then on the vertical axis, we have the frequency. So here we have the points, here we have the frequency, And the highest frequency we see is 11, so we need to at least go up to 11. So let's have 10 here, then 5. And then we just draw a bar to the right height for each category. In the first class, the frequency is 5, so we'll draw a bar up to 5, ranging from 0 to 5. Then from 5 to 10, the frequency was 11, so that one goes all the way up to the top of the graph. Then from 10 to 15, that frequency was again 5. From 15 to 20, it goes down to 4, so we'll draw it a little shorter, down at the tick mark for 4. And the last one goes back up to 5. So each class, each category, gets a bar with the height representing the frequency. It's relatively simple once you've drawn the frequency table, which just consists of counting the ones that fit into each class. Here we'll build a bar chart for this data set, which is the positions for the players in the NBA sample. Again, we have 30 observations falling into one of 5 categories: point guards, shooting guards, small forwards, power forwards, and centers. First, we need to find the frequency of each category, which means building the frequency table. But since we've already done that in a previous example, I won't go through in detail and count those. Rather, we'll just put the results here in this frequency table. We have the 5 positions and the frequencies. There are 4 point guards, 9 shooting guards, 7 small forwards, and 5 power forwards and 5 centers. Now, just like with a histogram, we start with our grid, and this time the horizontal axis will represent, again, our categories. So we'll have 5 spots for our bars to go. And then the vertical axis will again represent frequency. So the horizontal axis is position, the vertical axis is frequency. The highest frequency we see is 9, so we need to make sure we go up to at least 9. Let's again go to 10. And now we're ready to draw a bar for each position. So rather than having the bars connect like they would with a histogram, with a bar chart, since we're thinking of these as separate categories, they're not ones that flow into one another, we'll draw the bars with some separation. So at the point guard position, we'll draw a bar that goes up to 4, since there are 4 of those. And then at the shooting guard position, we'll draw one that goes up to 9. Small forwards have a frequency of 7. And power forwards and centers each have a frequency of 5. So again, we're drawing a bar where the height represents the frequency of that category. But unlike with a histogram, these bars are separated because we're indicating that these are separate categories and there's not a flow from one to the next. Let's build a stem and leaf plot. The question says, suppose you gathered data on how long it took you to get ready in the morning. For 40 days, you measured the amount of time between when your alarm went off and when you left the house. The results are below, rounded to the nearest minute. And we want to build a stem and leaf plot for this. For a stem and leaf plot, we divide each value into its stem and its leaf. And the stems are generally the tens place, although you can tweak this and make it, for instance, the ones place. But in this case, since our values are 2-digit values, the first digit will represent the stem and the second digit will represent the leaf. So if you look through, you'll notice that all of these numbers start with either 1, 2, or 3. That's the first digit. So our stems could be 1, 2, or 3. And now we'll go through, and for each value, we'll place that leaf in the correct category. So the first value is 35, so we'll put a 5 under the leaves category in the third row. Then for 28, we'll put an 8 here. Then 25, we'll put a 5 here. Then 23, and so on. We'll put another 3. Then 32 means we'll put a 2 in the third column. Then 29, 19, 21, 13, and so on. And I won't go through and fill all these out in detail. I'll go through and show the final result in just a moment. Now what you often find with a stem and leaf plot is that we write the leaves in the order of their value rather than the order in which they appear in the data set. So instead of writing 8, 5, 3, 3, 9, 1, we would write the 1 first, and then the 3s and the 5s and so on. Now this takes some extra work because we have to do some sorting, but when I show the results in a second, it'll be shown in that way with them sorted by value. Now that we have all the stems and leaves written, notice how it looks. It looks almost like a histogram or a bar chart turned sideways, where the length of each string of leaves represents the frequency of that category. So it divides it into categories by tens, and we can see that the most frequent category is the range from 20 minutes to 29 minutes. And yet, unlike a normal grouped frequency, by grouping them, we haven't lost any information. We could reconstruct the entire data set from this stem and leaf plot if we had to. In this example, we'll construct a scatter plot for some data that we're given. We're given the sizes of several TVs and the price that goes along with each one. Now our data is separated into 3 categories just so that the table could fit easily here, but side by side you'll see a size and a price where the size is given in inches and the price is given in dollars. And we want to construct a scatter plot where we compare these 2 variables. Now when we construct a scatter plot, we have to pick which variable will be x and which one will be y. It's not crucial that we pick it in the right order because it turns out if they get switched, much of the analysis we can do is still the same. But if we can, it would be nice to pick x and y in a reasonable way. And usually we want to think about how x determines y. In other words, is there one of the variables that seems to control the other one? Would we say that the size determines the price of the TV, or would we say that the price determines the size? It's probably more likely that we would say that the price depends on the size, or that the size determines the price. So we could call x the size and y the price. So let's say our x-axis represents size and our y-axis represents price. Again, we'll try to be consistent with these where the first column is x, the second column is y, but it turns out that if you switch the order, it doesn't change too much, at least at this point. So now we need to put a scale on each axis. So for the sizes go up to about 60 inches. So let's make sure we include at least up to 60. Let's say we go up to 70 here. And if we start down at 0, that means we need to divide this evenly so that we get to 70. So halfway there would be 35. And then if we divide these by 5s, 3, 5, 10, and so on. Then the prices range from 200 to about 2,800. So let's say we include all the way up to 3,000. And let's mark it in increments of 500. Now for each value in our list, let's take the first one for instance. The size is 43 inches, the price is $500. So on the horizontal axis, the size axis, we'll go up to 43, which is around here, between 40 and 45. And then on the price side, we'll be right at 500. So we want to find out where those two cross, which is right around here. So our first point will be right there at 43 inches and $500. For the next one, we'll go to 55 at $900. So 55 is right here between 50 and 60. $900 is right here, right under 1,000. So those two look like they cross right around here, which gives us our second point. And then we'll continue for the rest of them without showing each one in detail. I'll just show the final picture here in a moment after we've drawn all these points. So there's the final result, and even though it's hand-drawn and imperfect, we can see the general trend, which is that larger TVs tend to cost more. So there's this general upward trend as you scan through this picture. And that's really the value of a scatter plot, is to look for an association or a connection between 2 variables to see if there's a relationship. And this one looks like there's this upward trend. Later on, we'll talk about how to draw a line or some other curve that represents this shape. But for now, just notice that there's that relationship between the two. Find the median of the salaries listed below. So these are the salaries from the MBA data set. We have 30 values, and we want to find the median. Remember that the median is the middle data point. Now, helpfully, these salaries have been listed for us in order from smallest to largest. So notice we have the smallest value here, and then they increase along this row, and then down to the next row until we reach the largest value at the bottom right. And that's important when you're finding the median, to order them from least to greatest or from greatest to least, so that when we look in the middle of that list, the middle value is truly in the middle between the highest and lowest, so that half of the data points fall below it and half of them fall above it. So since it's listed like this for us, we can look halfway through. Since there are 6 rows, at the end of the 3rd row and the beginning of the 4th row, we have the middle. So the middle is right between this value and this value. Since there are 2 values in the middle, which will happen every time we have an even number of data points, we need to find the number halfway in between those two, which we do by averaging them together. So find the average of those 2 numbers in the middle, that will be the median. If we had an odd number of data points, like say we had 29 players, we would find the middle value and that would be our median. We wouldn't have to find any average. But anytime there's an even number, there will be 2 in the middle, so we need to find whatever is halfway in between those 2. So the median will be halfway between 4,469,160 and 4,767,000. So if we add those together and divide by 2, what we get is 4,618,080, and that's the median. Half of the players make less than 4,618,000, half of the players make more. So that's the middle data point, and it's a good measure of the center. Here we'll find a weighted average using a student's score in a class. So we have several assignments, 3 tests, homework, project, and final exam, and we're given the student's score on each of these assignments, as well as a weight for each assignment or a number of points for them. Now notice that usually we'd be given either the weight or the points. In this case, we're given both, and if you look closely, there are a total of 1,000 points that they could earn. If you add up all those points, you should get 1,000. And if you divide each of those point values by 1,000, you'll get the percentages that are listed here. So really, the same information is given in the weight column or in the points column. And you may see for some of your classes, the scores are given with weights. Sometimes they may be given with points. It's really the same thing. It's just written in a different way. So we're going to show the calculation with both just to compare, but we'll get the same answer either way. For part A then, let's use the weights. So for the weights, we can multiply each score the student got by the weight that's associated with it. And once we multiply those and add them all together, the answer we'll get at the end is the average score. So the weights are nice because they're already scaled for us, so that just by multiplying the score times the weight and adding those together, we'll get the final weighted average. So all we have to do is take 85% times 20% plus 92% times 20% plus 87% and so on. So if we multiply all those and add them all together, the answer we get at the end is about 0.899, which works out to 89.9%. So on a standard 10-point scale, this student will be very close to an A, just under 90%. Now let's do the same thing with a point system. And we're going to get the same answer, of course, but this time we have to do 2 steps, where first we multiply their score. So for the first category, they got 85% times the number of points they got, and then do that for all of them. And once we multiply and add all those up, we get 899 points. So they earned a total of 899 points, and then when you divide that out of the total of number of points they could have earned, which was 1,000, they get 0.899, which again works out to 89.9%. So notice you're doing the same work both ways. It's just that when you use the weights, you've already divided by 1,000 before you start. When you use the points, you have to divide by 1,000 at the end to get the final score the same way you did with the weights. So either way you do it, you're using the same values, and this is how you do a weighted average, whether you're given the weights as percentages or as points out of a total that you could earn. Here we'll find the mode of a data set that's summarized for us. We're already given the frequency table rather than just the raw data, so most of the work is done for us. The mode is the most frequent data value. And the nice thing about having the data given to us as a frequency table is all we have to do is look through the frequencies and find the highest frequency. Notice the highest frequency is 4 and occurs 3 times. There are 3 values which occur 4 times and are tied for most frequent, and those are 21, 22, and 24. So there are actually 3 modes, and this can happen a lot. In our case, the modes are 21, 22, and 24. Here we'll find the range of a data set that we're given, and the data set is the heights of the players given in the NBA data set. The range is really simple. It's just the difference between the smallest and the largest. So all we have to do is look through this list and find the smallest number and the largest number that occur. If you scan through, you should be able to pick out that the lowest number is 1.78. 1.78 meters is the shortest player in the sample that we listed. And the tallest player is 2.13 meters. So the range is just the difference between those two. If we take 2.13 minus 1.78, the range is the difference, or 0.35 meters. That's a really simple way of measuring how spread out the data is. If the range is larger, it's more spread out. If the range is smaller, it's more tightly clustered together. So 0.35, when compared to the values in this data set, is a fairly small range. So they're fairly tightly clustered together. All of these players are relatively tall.
Here we'll calculate the standard deviation by hand using the formula instead of using the built-in function in the calculator, just to illustrate how the formula works. We have 5 data points and we want to calculate the standard deviation. The first thing we need to do is to calculate the mean. So the mean, remember, is the sum of the data points divided by the number of data points. So we add them up and divide by 5, and we find that the mean is 10.2. Now, the standard deviation of this data set is the square root of the sum of the squared deviations divided by n minus 1, and all of that's inside the square root. So we'll need to calculate these things individually. We need to find each deviation, the difference between each data point and the mean, square those, add them up, divide that answer by n minus 1, and then take the square root of that answer. So this can get kind of tedious, which is why we only do this with small data sets. And from this point on, we'll use the built-in function in the calculator, but here we'll just illustrate the formula once. We'll use this table to organize everything. We have the data values listed, and we'll calculate the deviation for each one by simply subtracting this number, 20 for instance, minus 10.2, and then 4 minus 10.2, and 15, and so on. And we'll calculate a deviation for each data value. Once we've done that, we square them all. And remember, the reason that we square them is because if we try to average these deviations, we would get 0, because the positive ones and the negative ones would cancel each other out. But by squaring them, we end up with all positive numbers, so when we average those, they don't cancel each other. Then here all the squared deviations are filled in. Now, we need to add those squared deviations, divide by n minus 1, or 4 in this case, and then take the square root of the answer. Adding these all up, we get 210.8, and then if we divide that by 4, we get 52.7. But we're still not done. The last step is to take the square root of that. The square root of 52.7 is 7.26. So the standard deviation of this data set is 7.26, or the distance that a typical data point is from the center. Again, this example mostly illustrates why we don't calculate the standard deviation by hand usually. Even for a small data set, it gets pretty tedious.
A random sample of 11 statistics students produced the following data, where X is the third exam score out of 80, and Y is the final exam score out of 200. Here we'll use a graphing calculator to find the equation of the least squares regression line so that we can predict the final exam performance, which is Y, based on the third test score, which is X. So to use the calculator, we first need to enter the data. if we enter the stat menu and edit, we can enter the data here, which I've already done. The first list, we've entered the x's, and in the second list, we've entered the y's. Now, if we go back under the stat menu, we want to calculate, so we'll scroll over to the calc menu, and we want linear regression. The form we've been using is this number 4, linreg ax plus b. So a is the slope and b is the y-intercept. If we select that, we don't need to change anything here because we entered the x's in list 1 and the y's in list 2. So nothing needs to be changed. We can just scroll down to calculate, and it gives us the equation. The form of it is y equals ax plus b, and we get the values for a and b, as well as values for r squared and r. And now we have a better sense of what this r represents. That's the correlation coefficient. So the correlation coefficient is about 0.66, which means there's a moderate linear relationship, and it's positive. So there we go. There's our regression line, and there's the r value that goes with it. Here we're given a regression equation, which we developed in a previous example, to predict the price of a house based on its square footage. So if x represents the square footage, we can predict the price in thousands of dollars. So if we entered 1,000 for the square footage for x, we could calculate a value for y that would be the predicted price for houses with that square footage. And we're going to use this equation to predict the price of homes with 2 different square footage values. So all we have to do in each case is replace x with the given value for square footage. In the first case, we have y hat equals 0.099 times 2700 plus 160.8, which works out to 428.1. So that corresponds to $428,100. And that technically means that the average house price we would expect for all the houses that are 2,700 square feet would be $428,000 approximately. And then in the second case, we can make a similar prediction for houses with 4,500 square feet. And that works out to just over 600,000. Then the question asks, which prediction do you expect to be more reliable? Now for this, we'd really have to go back and look at the data, which we don't have in front of us. But if you go back in the textbook and look at the data, you'll notice that in the range of houses that we have data for, 2,700 square feet falls within that range, and 4,500 square feet does not. None of the houses we have in our data set are nearly as big as 4,500 square feet. So it turns out that the first one is more likely to be reliable without extra information. For all we know that now, it seems more likely that the first prediction would be more reliable because we've seen houses that are similar to it in our data set. The first example we call interpolation, where we are predicting within our data range. The second one we call extrapolation, where we're predicting beyond our data range. And in general, extrapolation is dangerous because we don't know quite what could be happening beyond the range of data we've actually looked at. So in general, interpolation is more reliable than extrapolation. So the first prediction is more likely to be reliable, even though we don't have a lot of information about it at the moment. Here we'll do a linear regression problem with several steps. First, we're given some data, which is a set of quarterbacks in the NFL during the 2019 season. And for each quarterback, we're given their height and their weight. We're going to compare these two. Now, without any other information at the moment, we're going to assume that height is going to represent X and weight will represent Y, just because they're ordered that way. Later on in the problem, we might have more information that'll tell us which one should be X and which one should be Y. But for now, we'll just assume that and change if necessary. So first, we want to calculate the correlation coefficient. And to do this, we'll use the calculator. So first, we need to go to the calculator and enter this data. To enter the data, we'll hit the Stat button and hit Enter to get into the Edit menu. And under List 1, we'll enter the X values. So the heights that we saw, the first quarterback had a height of 75 inches, then 74, 74, 70, 71, 74, 76, 77, 72, and 74. And then we can scroll over to the second list for their weight, and we'll enter these as well. Once we have all the data entered, we can go back into the stat menu and scroll over to the calc, down to the linear regression option. Again, we've entered x's in list 1 and y's in list 2, so we don't need to change anything. If those were switched, it wouldn't change the correlation coefficient anyway, so for this first part, it didn't really matter which way we entered them, but later on it will be significant. So we'll just hit calculate, and it goes ahead and gives us the equation for the line, which we don't need just yet. All we're looking for at the moment is the value of r, which is about 0.6. The first part of the question just asked for the value of r, so now that we have that, we can go back to the notes and enter that. Now for the second part of the question, we want to know, is there a strong linear relationship? So based on the value of r, we know first of all that there is a positive relationship, since r is positive, and we wouldn't necessarily say it's a strong relationship because it's less than 0.8, which again is not a magical number, but it's sort of an agreed upon level for a strong relationship. But 0.6, we might say there's a moderate relationship. And often a moderate relationship is good enough to continue on, and we'll continue to do the rest of the problem. So we wouldn't necessarily say it's a strong relationship, but it is a moderate linear relationship. The next part of the question asks for the regression line, which we've already calculated. Now notice the direction here. The regression line is going to predict the weight from the height. In other words, the weight is going to depend on height, which means that weight should be y and height should be x, which is the way that we already set it up. So it's good that we did so, and the regression line that we got from the calculator earlier is the one that we'll write here. So if we go back to the calculator, we can see what we had there. We have A is about 3.01 and B is negative 4.43. So now that we have that, we can move on to the rest of the problem. Here we want to graph the data as well as the regression equation. And I'll actually use the calculator to do this. We'll graph both the data and the equation on the same window. We already have the data entered, so if we turn on the stat plot under second y equals, we turn on this first stat plot and leave it as a scatter plot the way it is. X and Y are in the right order. Now when we graph, we'll see those points as long as we're scaled to the right window. And then also, if we hit y equals, we can graph the equation, which was 3.01x minus 4.43. Now before we graph, we should go to the window and make sure that our x values and y values are in the right range. The x values, the heights range from 70 up to 77, so we should make sure that x covers at least that range. So let's say we make x min 68 and x max 79. And then the y values, the weights, range from 200 up to 233. So let's say we go from 190 to 240. Now when we graph this, we see those heights as well as the line that passes through them. Now notice what this graph gives us. First of all, it points out that outlier on the lower right-hand side. And that's the first entry. Lamar Jackson is on the upper end of the height scale. He's at 75 inches. He's one of the taller players, but he's actually the lightest of all of them at 200 pounds. So if we actually removed him from the data set, our R value would be much, much higher, because he's what's making the data points not follow a straight line. Since he's kind of out in space by himself, that messes up some of the strength of the linear trend that would be there otherwise. So sometimes there are outliers like this that will lower the value of R, but if you remove them, the value of R will be better. Of course, you can't just throw away outliers because your data would look better without them, but keep that in mind. Next, we can predict the weight of a quarterback who is 73 inches tall. So given a height, we can predict their weight using this equation. So A is 3.01, and then if we plug in 73 for X, we can predict that Y hat, their weight for a quarterback of this height, would be about 215 pounds. Lastly, we get this question: does Drew Brees weigh more or less than the weight predicted by the regression line based on his height? So we can do the same thing we did in the last part, where we predict what someone who is the height of Drew Brees, 72 inches, would tend to weigh according to this equation. And according to this equation, that comes out to 212 pounds approximately. So the question asks, does he weigh more or less than the predicted value? The predicted value is 212 pounds, and he only weighs 209 pounds, so he weighs less than what's predicted. So here are the answers to all the parts of this question. We found the correlation coefficient, we interpreted it, we found the regression line and graphed it alongside the data, and then we made a couple of predictions based on that regression line.
The scores on a college entrance exam are normally distributed with a mean of 52 points and a standard deviation of 11 points. And we're asked to find what two scores encompass 95% of the test takers. Since the data is normally distributed, the empirical rule tells us that 95% of the data will be within 2 standard deviations of the mean. Since 1 standard deviation is 11 points, 2 standard deviations is 22 points, twice that. So 52 minus that and 52 plus that will form the boundaries of this range that includes 95% of the data. Therefore, we decide that 95% of the values lie between 30 and 74. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. Here we're asked to use the empirical rule to find the data that is within 1, 2, and 3 standard deviations of the mean. Remember, the empirical rule states that 68% of the data is within 1 standard deviation of the mean. Meaning that if we go 1 standard deviation below the mean and 1 standard deviation above the mean, that range will hold 68% of the data. 95% of the data falls within 2 standard deviations. And almost all the data, or around 99.7% of the data, falls within 3 standard deviations. So if we work from the mean down 3 standard deviations and up 3 standard deviations, will encompass almost all the data. In this case, with a mean of 100 and a standard deviation of 15, 1 standard deviation below will be 85, and 1 standard deviation above will be 115. 100 minus 15, 100 plus 15. So 68% of the data, in other words, 68% of people will have an IQ score between 85 and 115. 95% of people will have an IQ score between 70 and 130, and almost everyone will have an IQ score of between 55 and 145. Here we have a picture that illustrates this situation, where each unit on the axis is 1 standard deviation. Suppose you know that the prices paid for cars are normally distributed with a mean of 17,000 and a standard deviation of 500. We want to use the 68, 95, 99.7 rule, or the empirical rule, to find the percentage of buyers who paid in any given range. The first thing to do when working with a problem like this is to draw a picture. And here's the picture for this example. The center is the mean, and then each unit on the axis is the standard deviation. So we have it centered at 17,000, we go up to 17,500, 18,000, 18,500, and we could keep going, but that's all we need. And then on the lower side, we go down to 16,500, 16,000, and 15,500. Here I've also filled in all the percentages for each range. Notice that the empirical rule tells us that 68% of the data falls within 1 standard deviation of the mean. Since everything is symmetric, each half of that holds half of that 68%, and that's where those 34% numbers came from. Then I know that within 2 standard deviations of the mean, I have 95% of the data. If I have 68% in the middle, and by going out another standard deviation, I get to 95%, that means the yellow regions together must make up that 27% that gets us from 68% to 95%. So if the 2 yellow regions together hold 27%, each of them holds half of that, or 13.5%. We can repeat this process for the green regions. Again, going out to a third standard deviation, we know that that holds 99.7% of the data. So the green regions together must hold 4.7% of the data, since everything up through the yellow regions held 95, and then just by adding the two green regions, we got to 99.7. The green regions must be that 4.7%. Therefore, each of them holds half of that, or 2.35%. And then outside the 99.7 is 0.3% of the data, and again, because it's symmetric, each half of that, or each tail, contains 0.15%. Again, the goal is not to memorize these percentages, but just to realize how we got them and be able to rederive them at any point. But now that we have them, we can use them to solve the problem. So, part A asks what percentage of buyers paid between $16,500 and $17,500. So we find those 2 points on our picture, and between them, we add up the blocks and find that 68% of buyers were in that area. Similarly, for part B, between $17,500 and $18,000, we locate those points, and between them, there's just one region with 13.5%. For part C, we look between $16,000 and $17,000, and there's 2 blocks there. Adding them up, we get 47.5%. For part D, we're looking between $16,500 and $18,000, and adding up those 3 blocks, we get 81.5%. So 81.5% of people paid somewhere between $16,500 and $18,000 for their car. Part E asks what percentage paid below $16,000. So that's right here. And below $16,000 we have 2 blocks to take care of, 2.35% and 0.15%. Adding them together we get 2.5%. So 2.5% of buyers paid less than $16,000 for their car. Lastly, the final part asks what percentage paid above $18,500, and again there's only 1 block up there, so 0.15% of buyers paid above that amount. And here we have all the answers summarized. Here we're told that female adult height in some population is normally distributed with a mean of 65 inches and a standard deviation of 3.5 inches. And we're asked to find the z-scores of 2 heights. Remember that a z-score is the data value minus the mean divided by the standard deviation. And this z-score represents how many standard deviations this data point is above or below the mean. If the z-score is positive, it's above the mean. If the z-score is negative, it's below the mean. For the first example then, to calculate z, we take 58 minus the mean, 65, and divide by the standard deviation, 3.5. 58 minus 65 is negative 7, and that divided by 3.5 is negative 2. So what that means is that first data value is 2 standard deviations below the mean. For the second point, we do the same thing, now taking 71 minus 65 and dividing by 3.5. 71 minus 65 is 6, and that divided by 3.5 is 1.71. So the second data point is between 1 and 2 standard deviations above the mean. Scores on an IQ test are normally distributed with a mean of 100 and a standard deviation of 15. We're asked to find the IQ score that corresponds to each of the following z-scores. So here we're given z-values, and we're asked to work backward from them to the data values. Again, remember though that a z-score is simply a given data value minus the mean divided by the standard deviation. Here we're given a z-score, the mean, and the standard deviation, and asked to solve for the data value. For the first one, for example, we know that z is negative 1.5. The data value is the unknown part that we're going to find. So the z-score is x minus the mean, 100, divided by the standard deviation of 15. Now to solve for x, I'm going to multiply both sides by 15, and we find that negative 22.5 equals x minus 100. Then add 100 to both sides to get x equals 77.5. So a z-score of negative 1.5 corresponds to an IQ score of 77.5. For part B, we do the same process. The z-score equals the data value minus the mean divided by the standard deviation. So we multiply both sides by 15 and find that 30.75 equals x minus 100. And then adding 100 to both sides, x equals 130.75. So a z-score of 2.05, or just over 2 standard deviations above the mean, corresponds to an IQ score of around 130. This question asks, what is the margin of error on a poll with a sample size of 1,000 people? With the simplifying assumptions that we've made, the margin of error is 1 divided by the square root of the sample size as a percentage. So this will give us a decimal, and then we'll write it as a percentage. To do that, some people write that this times 100% is the margin of error. And that times 100% just converts that decimal into a percentage. Again, there's some simplifying assumptions that lie behind this, but for our purposes, this is good enough. In this example, n is 1,000, so the margin of error is 1 divided by the square root of 1,000 times 100%. 1 divided by the square root of 1,000 is 0.0316, etc. And by multiplying by 100% or converting to a percentage gives us 3.16% approximately. It's fairly common for a poll to have a margin of error of around 3%, and when you see that, you can tell that the sample size is around 1,000 people.
In this example, we're going to find the sample size that corresponds to a given margin of error. So if we want a poll to have a margin of error of 2% or less, what's the minimum sample size needed to make that happen? Remember, the margin of error looks like 1 over the square root of n as a percentage. So we can write times 100% just to indicate that we're making it a percentage. So if we want this to equal 2%, then really what we want is we want 1 over the square root of n to equal 0.02. So as a decimal, we want 1 over the square root of n to equal 0.02, or as a percentage, we want it to equal 2%. Now we need to solve for n, and it takes a little bit of algebra to do so. There are a few ways to observe this. One, if we want to get n by itself, we could move it out of the denominator by multiplying it on both sides. So if we multiply it over there, we get 1 equals 0.02 times the square root of n. And then, again, we're trying to get this part by itself, so we'll divide both sides by 0.02, which gives us 1 over 0.02 equals the square root of n. Now, there's a shortcut to this. At this step, you could say we have 1 over the square root of n equals 0.02. You can actually flip both sides of that equation upside down and get square root of n over 1 equals 1 over 0.02, which gets you to the same place that we already did, just by a shortcut. Don't get too lost in that step if that doesn't make sense, but there are shortcuts to some of this algebra. Once we get to this point, though, we just have one step left, which is that we need to square both sides. Now before I do that, I'm going to simplify 1 divided by 0.02, and that simplifies to 50. But now to get rid of that square root, we just need to square both sides. And the square root will cancel each other. When we square 50, we get 2,500 equals n. So that's our answer, that if we sampled at least 2,500 people, we would be guaranteed to have a margin of error of 2% or less. And if we sampled more than 2,500, our margin of error would be less than 2%. But as long as we sample 2,500, we'll be guaranteed to have a margin of error of 2%.
Consider randomly selecting a family with 2 children where the order in which different gender siblings are born is significant. That is, a family with a younger girl and an older boy is different from a family with an older girl and a younger boy. What would the sample space look like for this family? In other words, what are the different possibilities for children that this family could have? Remember, the sample space is a list of all the possible outcomes. Well, in a family with 2 children, either they could both be girls, or they could both be boys, or you could have one girl and one boy. Now, we're told that the order matters, so having a girl then a boy is different than having a boy then a girl. So these are the 4 possibilities, and that's our sample space. Suppose we toss a fair coin and then roll a 6-sided die once. Describe the sample space S. Again, the sample space is a list of all the possibilities for what could occur. If we're flipping a coin and rolling a die, then we can think about it this way. Either the coin is going to be heads or tails, and then the die is going to be a number from 1 through 6. So let's suppose the coin comes up heads. Well, then the number could be 1, or it could be 2, or 3, or 4, or 5, or 6. And then the coin could come up tails, and the die could be either 1, 2, 3, 4, 5, or 6. So we have 6 more possibilities with the coin coming up tails. And that is a full list of all the possibilities that could occur with this experiment. Assume you're rolling a fair 6-sided die. What is the probability of rolling an odd number? Remember, a basic probability is the number of ways that our event could occur. So in this case, the number of ways to roll an odd number divided by the number of total possibilities for what could occur when we run this experiment. So all we have to do is count up how many ways this event could happen and count up the number of total possibilities, and then divide the two to get the probability. So our sample space, or our list of total possibilities, is the numbers 1, 2, 3, 4, 5, and 6, because those are the outcomes that we can have when we roll a die. Of those, 3 of them are odd numbers, the 1, the 3, and the 5. So there are 3 ways to roll an odd number, 6 total possibilities, so the probability is 3 out of 6, which we could simplify to 1/2, or we could write as 0.5 or 50%. Any one of them is an acceptable answer. And of course, at the beginning of this problem, you might be able to think about it and realize that the die is going to come up either an even number or an odd number, and since there's an equal number of even numbers and odd numbers, the chance that it comes up odd is 1 out of 2. And that again illustrates that there are often many different ways to solve a probability problem, and as long as you use one of the correct ways, everything's fine. Suppose you draw 1 card from a standard 52 card deck. What's the probability of drawing an ace? Here I've put a picture of a standard 52 card deck, just for reference. Again, we have 4 suits, the clubs, hearts, spades, and diamonds. Within each suit, there are 13 cards, ace, and then the numbers 2 through 10, and then the 3 face cards, jack, queen, king. So we've got 52 total cards to draw from, so the number of possibilities, or the denominator in our probability, is going to be 52. Now, out of those 52 possibilities, 4 of them correspond to drawing an ace, because there are 4 aces. So, the probability of drawing an ace is simply 4 out of 52. Lisa's cookie jar contains the following: 5 peanut butter cookies, 10 oatmeal raisin, 12 chocolate chip, and 8 sugar cookies. If Lisa randomly selects 1 cookie from this jar, what is the probability she gets a peanut butter cookie? Again, probability is simply the number of ways that our scenario can happen, so in this case the number of peanut butter cookies in the jar, divided by the number of total possibilities for what could happen, so the total number of cookies. So all we have to do is count the number of cookies in total, divide the number of peanut butter cookies by that, and that's our probability. If there are 5 peanut butter, 10 oatmeal raisin, 12 chocolate chip, and 8 sugar cookies, that's a total of 35 if we add up those 4 numbers. And there are 5 peanut butter cookies, so the probability of drawing a peanut butter cookie is 5 out of 35. The number of ways that can happen divided by the total number of possibilities. Once we have that, we can either leave the answer this way, or we can simplify the fraction to 1/7, or write it as a decimal or a percentage. Again, any one of them is fine, as long as we get the right number. Consider the following information about students' enrollment at FCC. We have a table that breaks down the gender of students, and we're told how many male students there are and how many female students there are. Then we're told that we randomly select one person from all these students, and we want to know what is the probability that the one we selected is a male student. Well, again, the probability is simply the number of ways that that could happen. Well, out of this group, there are 2,580 ways to select a male student, because that's how many male students there are. And there are a total of 6,233 students. And I got that number by adding together the female students and the male students. So that's the probability, and written as a decimal, that's approximately 0.414. Here we're given a breakdown of some students at FCC by their residence. So some live in Frederick County, some live out of county, some live out of state, and some are employees of the college. Furthermore, we're told that each student can only be assigned to one category, so there's no overlap. No one falls into any two categories. We randomly select a person from this group, and we want to know what the probability is that that person we selected is from out of county. So we're looking at this second category. Well, again, the probability is the number of ways that could happen. So 245 is the number of people that we could select in that category, and then divided by the total number of people there are. So if we add up the 5819, the 245, the 141, and the 28, we get a total of 6233. So that's the probability, the number of ways of selecting an out-of-county student divided by the number of ways of selecting any student. And again, if we write that as a decimal, we get about 0.039. This example has what's called a contingency table, or a two-way table. So we have 130 FCC students broken down by gender and by dominant hand. So there are male and female, and then right-handed and left-handed. And since we're breaking them down by two categories, there are four total possibilities: female right-handed, female left-handed, and then male right-handed and male left-handed. We're also, helpfully, given these totals for each row and each column. If we weren't given those, we could easily find them. For instance, the total right-handed is simply the male right-handed plus the female right-handed. Adding those together, we get 105, and so on. You can add up each row and column. And then once you have these row and column totals, if you add together the two column totals, you get 130, and if you add together the two row totals, you also get 130. And that's a nice check to make sure that everything works out and that you haven't added something incorrectly. Now though, we're asked, if we randomly select one person from this group, what is the probability that this student is left-handed? So all we have to think about is the number of ways that we could select a left-handed student divided by the total number of ways that we could select any student. Well, the number of ways to select a left-handed student is just the number of left-handed students there are. So if we go to the left-handed column, we notice the total there is 25, which again we could have gotten by adding the 13 and the 12. So there are 25 left-handed students, so 25 ways to select a left-handed student, and there are 130 total students all in all. So the probability of selecting a left-handed student is 25 divided by 130. And if we write that as a decimal, it comes out to about 0.192. Here's a simple example to demonstrate the law of large numbers. Again, the law of large numbers states that if we do an experiment over and over and over again, the results will line up with the probabilities that we expect before we run the experiment. It's similar to one of the ways that we define probability. For instance, we could define the probability of flipping a coin and getting heads as 50% by saying that if we did this over and over and over again, the proportion of heads that we would get would be 50%. Here, though, we'll illustrate this law. So consider this experiment. Let's roll a six-sided die over and over and over again and take the average of the results that we get. For instance, for the first 10 results, we might get something that looks like this table, where we get a 4 the first time, then a 2, then a 1, then a 6, and so on and so forth. If we average together these results, we get 3.3. If each number from 1 through 6 is equally likely, we expect to get the middle number as our average, while the middle of those 6 numbers is between 3 and 4, so 3.5. So our expected result is 3.5 as the average for these rolls. So after 10 rolls, we've gotten pretty close. We got to 3.3, but the law of large numbers says if we do this more and more times, we should get closer and closer to the average of 3.5. Here's a graph of what happens if we roll the die even more times. after just a few rolls, there's some volatility in the results. After maybe the first 10 rolls, the average might be as low as 3, but over time, as we roll the die more and more times, taking the average after each roll of all the rolls up until that point, slowly this average will start to creep back toward 3.5, toward the expected value. So it may diverge a little bit, but eventually over time it's going to settle down to that average. So the law of large numbers essentially says that in the long run the average will be 3.5. Even if in the short term it isn't quite that, over time it'll settle down to that average, and over time these results get closer and closer to the average that we expect. And that's the law of large numbers, that over time the empirical probability that you observe approaches the theoretical probability that you calculate before ever running the experiment. Suppose you roll a fair six-sided die once. What is the probability of rolling a 6 or an odd number? There are a couple of ways to do this problem, and I'll do two. For the first, I'll use what we know about OR probabilities. We know that the probability of one event or another happening is the sum of their individual probabilities minus the overlap, minus what happens when both of them occur. In this case, a 6 and an odd number are mutually exclusive events. These events cannot happen at the same time. If you roll a 6, you didn't roll an odd number, and if you rolled an odd number, you didn't roll a 6. So the probability that both of them happen together is 0. So in this case, the probability of rolling a 6 or an odd number is just equal to the probability of rolling a 6 plus the probability of rolling an odd number, because there's no overlap, so that doesn't affect the calculation. The probability of rolling a 6, well, there's 1, 6, and 6 total numbers, so the probability of rolling a 6 is 1 out of 6. Rolling an odd, well, there's 3 odd numbers, 1, 3, and 5, and 6 total possibilities. Adding those up, we get 4 out of 6, or 2/3, or 0.67, or 67% if you like. The other way to do this problem is simply to list the sample space, or to picture it at least, and to think about how many outcomes correspond to either a 6 or an odd number. Well, all the odd numbers are 1, 3, 5, and then the 6 is the extra one. So there are 4 outcomes that correspond to the event that was specified, rolling a 6 or an odd number, and there are 6 total possibilities. So again, we get 4 divided by 6. Again, there's at least 2 different ways of doing this problem, and both of them give the correct answer. Both of them are perfectly fine ways of doing it. So either way you do this problem is okay. But for some problems where the sample space is so large that we don't want to list it or picture it, the first method will be more useful. Suppose you draw one card from a standard 52 card deck. What is the probability that you get an ace or a face card? Again, the probability with OR says that the probability of one thing or another thing happening is the sum of their individual probabilities minus the probability that they happen at the same time, minus the overlap. And again, the reason for that is that if you simply sum the probabilities of the individual events, you double count the overlap. So we have to subtract off the overlap once so that we don't double count it. Here, the probability that you get an ace or a face card, well, an ace is not a face card, so these events are mutually exclusive or disjoint. They won't happen at the same time. If we're only drawing one card, we're either going to get an ace or a face card or something else, but we're not going to get something that's both an ace and a face card. So in this case, the probability that we get an ace or a face card is simply the sum of their probabilities, because the probability of both of them happening together is 0. So we just subtract off 0 at the end, which doesn't change anything. The probability of drawing an ace, well, there are 4 aces. The ace of clubs, diamonds, hearts, and spades, and there are 52 total cards. The face cards, there are 3 face cards for each suit, the jack, queen, and king, and 4 suits total, so that's a total of 12 face cards out of 52. Adding them together, we get 16 out of 52. We could also simplify this down to 4 out of 13. And that's another way of thinking of it. You could focus just on one suit and say, well, in this suit, there's 1 ace card, 3 face cards, and so 4 cards meet the description that I was given out of 13 cards in this suit. So all the suits are the same, so my chances of drawing an ace or a face card are 4 out of 13. So again, there's multiple ways of thinking of this problem, multiple ways of analyzing it, but with all of them, if we think correctly, we get to the correct answer. Here we're given this contingency table, or two-way table, that contains information about 130 FCC students, broken down by gender and by whether they're right-handed or left-handed. We randomly select one person from this group, and we ask what's the probability that our randomly selected student is female or left-handed. So we're looking for the probability that they're female or left-handed. And again, an OR probability is the sum of the individual probabilities minus the overlap. Again, we have to worry about subtracting off the overlap in this case because these are not mutually exclusive. In other words, our randomly selected student could both be female and left-handed. We're randomly selecting from a group of 130 students, so that's going to be the denominator on each of these pieces. The number of ways to select a female student is 71 because there are 58 right-handed female students, 13 left-handed female students, for a total of 71 female students. The number of ways to select a left-handed student would be 25, since there are 13 female left-handers and 12 male right-handers. And again, the total number of people that we're selecting from is 130. The probability that our selected student is female and left-handed is 13 because there are 13 students in that category, 13 students that meet that description, and 130 total students. So we add up 71 plus 25, which is 96, subtract off 13, which is 83. So our final answer is 83 out of 130. And if we write that as a decimal, that's approximately 0.638. We could also think about this by adding up all the students that meet this description. So female or left-handed. Well, the female students, we add these categories up. And then the left-handed students are this column, but we've already counted these first 13, so if we just add on these extra 12, we'll add up all the students that are either female or left-handed. And notice if you add up 58 plus 13 plus 12, you get to 83 as well. The only category that isn't counted is the right-handed males, the only ones who don't fit this description of either female or left-handed. So again, multiple ways to get to the correct answer. Here's another contingency table, or two-way table. So here, a survey was given, and this table breaks down the number of people who responded to this survey, who have received or not received a speeding ticket in the last year, and then whether their car was red or not. So, speeding ticket, not speeding ticket, red car, not red car. And again, we're given the totals for each row and each column, but if we weren't given those, we could easily find them. We're asked to use this table, though, to find the probability that a randomly selected person from this group has a red car or got a speeding ticket in the last year. The probability that they have a red car or got a speeding ticket is the sum of those individual probabilities minus the overlap. Again, since these events are not mutually exclusive, since they can happen together, we need to consider the overlap and subtract it off. Since we're selecting from a group of 665 total people, that'll be the denominator for each piece. The probability they had a red car, well, the total number of people in this group who had a red car was 150. 15 of them got a speeding ticket, 135 didn't. But a total of 150 people in this group had a red car. The total number of people who got a speeding ticket is 60, because 15 people with a red car got a speeding ticket, and 45 people without a red car got a speeding ticket, for a total of 60. And then we need to subtract off the overlap, those with a red car and a speeding ticket. Because what we've done is we've added up this row and this column, which double counted this overlap, the overlap of 15. So we need to subtract off 15 out of 665. Again, we could also do this problem by adding up, for instance, those with the red car, and then only adding on the extra ones that we need. the people who got a speeding ticket but didn't have a red car. Or we could add up this column of speeding tickets and then simply add on the extra people who had a red car without a speeding ticket. Either way, we get to the answer that this probability is 195 out of 665. And if we write that as a decimal, it's approximately 0.293. So close to 30% of the subjects in this survey either had a red car or got a speeding ticket in the last year. If you pull a random card from a standard 52 card deck, what is the probability that it's not a heart? In other words, what is the probability that it's one of the other suits? The probability that something doesn't occur is always 1 minus the probability that it does occur. So we can either calculate the probability it does occur and subtract that from 1, like we're doing here, or we could think about the number of ways that we could draw a card that's not a heart and do it directly. I'll do it this way, though, using this formula. The number of ways to draw a heart, well, there are 13 hearts, 52 total cards. So the probability we don't draw a heart is 1 minus 13 out of 52, which ends up being 39 out of 52, which is exactly what we would find if we added up all the cards that aren't hearts. There are 13 spades, 13 clubs, and 13 diamonds. Adding those up, we get 39 total cards that are not hearts. And by the way, of course, this simplifies down to 3/4 or 0.75, which also makes sense. If 1/4 of the cards are hearts, 3/4 of the cards are not hearts. So the probability of not drawing a heart is 3 out of 4. A multiple choice question has 5 answers, and exactly one of them is correct. If you were to guess randomly, what's the probability of not getting the correct answer? This example is pretty simple, but we illustrate again how we calculate the probability that something doesn't occur. So the probability you don't get the correct answer is 1 minus the probability that you get a correct answer. Well, there are 5 total possibilities for what you could guess. One of them is correct, so 1 minus 1/5 is 4/5. So there's a 4/5 chance that you won't get the correct answer if you randomly guess. And of course, we can get to that answer directly by thinking about the fact that if there are 5 answers and one of them is correct, the other 4 are not correct. So when you randomly guess, you have 4 ways to choose an answer that's not correct, 5 total possibilities to choose from, so that probability is 4 out of 5. Again, multiple ways to get to the right answer, and any one of them is fine. But here we're illustrating the formula that lets us calculate the probability that something doesn't occur by taking 1 minus the probability that it does occur. According to the FCC website, female students make up 57% of the fall 2014 student body. If one student is randomly selected from the student body, what is the probability that that student is not female? Again, we're doing a probability of something not occurring, and that's always 1 minus the probability that that does occur. So 1 minus, now the probability that our randomly selected student is female is equal to the proportion of students that are female. So 57% as a proportion is 0.57. So we get 1 minus 0.57. Or if we were dealing with percentages, we could write 100% minus 57%, which would be fine. But either way, we get 0.43 or 43%. So again, if 57% of students are female, the other 43% are not. So the chances that we draw a student that isn't female is 43%. Determine whether these events are independent for each of these descriptions. Remember, 2 events are independent if they have no effect on each other. In other words, one happening has no impact on the probability of the other one happening. The first scenario says a fair coin is tossed 2 times. The 2 events are the first toss being heads and the second toss being heads. These events are independent because what happens the first time has no impact on what happens the second time. Each time the coin is flipped, it doesn't remember what happened the previous time, and it's an independent result. The second scenario says that the 2 events are that it's raining in Frederick, Maryland, and that it's raining in a nearby town of Thurmont. These events are not independent, because if it's raining in Frederick, it's probably also raining nearby. Those 2 events have some impact on each other's probability. The third scenario says you draw a red card from the deck, meaning either a heart or a diamond, and then you draw a second card without replacing the first. Now, if I drew a red card the first time, then the deck looks different than it did before I drew that card. Now there are 51 total cards, and only 25 of them are red. 26 of them are not red, which means that the probabilities for the second draw have changed, meaning these events are not independent. Because I didn't replace the card, the deck looks different, and so all the probabilities have changed. In the fourth one, though, if I draw a face card and then replace it and reshuffle the deck before drawing a second card, that makes the two events independent, because by replacing the card and reshuffling it, I've returned all the probabilities back to where they were. In other words, the deck looks the same as it did before I drew the first card. There's still 52 total cards, and all the cards are back in the deck. So those events are independent. So drawing without replacement, like in number 3, the events are not independent, but drawing with replacement, the events are independent, like in number 4. Suppose you flip a coin and then roll a 6-sided die once. What is the probability that you get tails and an even number? When we're dealing with probability with and, if the two events are independent, the probability of one and the other occurring is the product of the individual probabilities. Since these events are independent, we can do this. In other words, flipping the coin has no effect on what the die is going to do. So these events are independent. They don't change each other in any way. So the probability of one and the other is the product of their individual probabilities. The probability of flipping a coin and getting tails is 1 out of 2. And the probability of getting an even number is 3 out of 6. 3 even numbers and 6 total possibilities. Multiplying these together, it simplifies down to 1/4 or 0.25, or any equivalent fraction. So we could calculate the probability of these two things happening together by multiplying their probabilities, only because the events were independent. In this example, we'll draw without replacement from the population in the US. Now, before we said that drawing without replacement, the events are not independent. However, when we're dealing with such a large population, drawing one person out doesn't change the probabilities of the remaining pool enough to really matter in the problem. The change is so tiny that we can assume that it's negligible. So we're going to assume that these two trials are independent, even though we're drawing without replacement. And that's what that sentence in the middle of the problem statement says. About 9% of people are left-handed. Suppose 2 people are selected at random from the US population. Again, because the sample size of 2 is very small relative to this large population, it's reasonable to assume that these 2 people are independent. In other words, it won't change the problem in any significant way by assuming they're independent. What is the probability that both are left-handed? In other words, what's the probability that the first person left-handed and that the second person is left-handed? Well, of course, we can assume that they're independent, so this probability is the product of the 2 individual ones. Since 9% of people are left-handed, the probability of drawing a left-handed person is 9%, or 0.09. So we multiply together 0.09 twice, and we get 0.0081. So there's a little less than 1% chance that these 2 people that we select randomly are both left-handed. Assuming that the probability of having a boy is 0.5 or 50%, find the probability that a family with 3 children has 3 boys. So the probability of having 3 boys is equal to the probability of having a boy first, and a boy second, and a boy third. So these events are all independent. In other words, the first child has no effect on what the second child will be. We're assuming. So the probability of these events all occurring together is the product of the individual probabilities. And since the probability of having a boy each time is 0.5, we can multiply together 0.5 3 times. And what we get when we do that is 0.125. So about a 12% chance that this family will have 3 boys all in a row. Another way to do this problem is to list out the whole sample space of what could happen with 3 children. So boy, 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 girl, 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 boy, boy, girl, and so on and so forth. What you'll find is that there are 8 possibilities, and one of them is boy, boy, boy. So the probability of that happening is 1 out of 8. And 1 out of 8 is exactly 0.125. So either way we do the problem, we get to the same answer. If you pull 2 cards out of the deck, and the implication is without replacement, what is the probability that both are spades? As we said before, drawing cards without replacement means that the events are not independent, because once I've drawn the first card, that changes what the deck looks like for the second card. When the events are not independent, the probability of 2 things happening together is the probability of the first thing happening times the probability that the second thing happens given that the first one already occurred. Because if the first one didn't occur, it doesn't matter what happens the second time, the whole scenario has failed. But if the first card was a spade in this scenario, then we can continue forward and calculate the probability that the second card is also a spade and multiply those together. So in this case, the probability that the first card is a spade is 13 out of 52, because there are 13 spades, 52 total cards. If that first card that was drawn was a spade, there are 51 cards left because we drew a card, and 12 of them are spades, because the first one we drew was a spade. So we multiply the probability that we draw a spade the first time times the probability that we draw a spade the second time, assuming that the first card was a spade. So if we multiply those two together, we get, in decimal form, a probability of 0.0588, or about a 6% chance.
Here we're going to find the probability of several different events using a bag of M&Ms. We've got a breakdown of colors with the numbers listed of each color, and we're going to pull 2 M&Ms out of the bag without replacing the candy. So each experiment, we're going to pull 1 M&M out, hold it out, and then reach in and pull out a second one randomly. And then we'll reset the bag before the next experiment. So each part of this problem will assume we're starting with the same distribution of colors that are given here. So first of all, we want to find the probability that we'll draw 2 red candies, meaning that we'll draw 1, and then in our second draw we'll also get a red candy. So this is a multiplication rule problem where the 2 events are not independent. If we replace the candy and reshuffle the bag, then they would be independent because the probability on each draw would be consistent. But because we hold that first one out before we grab the second one, the events are not independent. And so we have to think carefully about what's going to happen with each situation. So the probability of drawing a red one and then another red one means that first of all we need to find the probability of drawing a red one on the first pull, and then multiply that by the probability that if we assume we did get a red one the first time, we'll also get a red one the second time. In other words, we assume that the first half of the problem went the way we needed it to continue going. If we drew a blue one, for instance, the first time, the experiment will be over because there will be no way to draw 2 red ones. So first we'll calculate the probability that the first one's red, then we'll assume that happened, and under that condition we'll find the probability that the second one is red. So the first one, there are 12 red candies, and if you add all the total counts together, you'll find that there's a total of 106 M&Ms in this bag to begin with. So the probability the first one is red is 12 out of 106. Now if we assume that happened, there are a total of 105 candies left because we're holding one out. And of those 105, only 11 of them are red if we assume that the first one was red. In other words, if we assume the first half of our experiment was successful, there's only 11 red candies left. So we calculate those 2 probabilities, and that second one is the conditional probability on the condition that the first one was also red. Now when we multiply those, we get 132 out of 11,130, which corresponds to about 0.0119. For the next part, we want to find the probability of first drawing a blue candy and then a brown candy in that order. So the probability of drawing blue, then brown, again is going to be the probability first of drawing a blue one, and then assuming that happened, the probability the second one is brown, given that the first one was blue. So again, there are 106 to begin with, and out of those, 22 of them are blue, If the first one we drew is blue, there are 105 total left, but all of the brown ones are still in there. If the first one we drew was blue, all the brown that were there at the beginning are still there. So there's still 24 browns. So if we multiply these together, we get 528 out of 11,130, which is about 0.0474. For the next part, we want the probability of not drawing 2 green candies. Now, if you try to do this directly, you'll find yourself getting lost very quickly because the number of ways you could draw not 2 green candies quickly gets out of hand. You could draw a red then a yellow, or a brown then an orange, or 2 browns, or a yellow and a green, and there are just too many possibilities to keep track of. It's much, much easier to first find the probability of drawing 2 green ones, and then remember that the probability of that not happening is just 1 minus that answer. So this is much, much easier. And then this one looks just like the ones we've done previously, especially part A. So we'll have 1 minus the probability that you draw a green one first times the conditional probability that you draw a green one second. So of course the probability you draw a green one first, there are 17 out of 106, and then assuming that happened, there will be 105 total, of which 16 will be green if you drew a green one the first time. So this is 1 minus 272 out of 11,130, which works out to 10,858 out of 11,130, or about 97 or 98%. For the last part, we're going to find the probability of drawing an orange and a yellow. Now this looks a lot like part B, where we drew a brown and a blue, but in part B, we were given an order specifically, blue then brown. In this case, notice carefully that order is not mentioned. It's just the probability that one of them is orange and one of them is yellow, which is easy to miss. But what we need to keep track of is that we could draw orange then yellow, or we could draw yellow then orange. And notice the word or tells us we're going to add the 2 probabilities together. So the probability of getting an orange and a yellow, we could do orange then yellow, or we could do yellow then orange. And these individual probabilities will do just the same way we did the previous ones. So for the first one, first drawing an orange, there are 13 out of 106. And then to draw a yellow, there will be 105 total. And if we drew an orange the first time, all the yellows would be left in the bag, all 18 of them. Then on the other hand, if we draw a yellow first, there would be 18 out of 106 times all the oranges, 13 out of 105. And if you notice carefully, those 2 values, this one here and this one here, are actually the same. So we could have just calculated the probability of orange then yellow, for instance, and then doubled it, and the answer would come out the same way as the one we're going to get in just a moment. So there are a couple of ways to do this, but this way keeps everything easy to see, and we can keep track of all the possibilities and make sure we're accounting for them all. It turns out this total is 468 out of 11,130, which is about 4%.
We're again given this data about the 130 FCC students, broken down by gender and whether they're right-handed or left-handed. Now, though, we're going to calculate conditional probabilities from this table. The first part asks, what's the probability that a randomly chosen student from this group is female, given that the student is left-handed? Now, if we're looking at a contingency table and we're dealing with conditional probabilities, we see the word given. The given tells us what category to restrict to. In other words, if we've drawn a student and we're given that this student is left-handed, we know that we're in the category of left-handed students. That given has restricted us to just that column. So we zoom in on that column and that's all we have to worry about. So the probability that the student is female, given that the student is left-handed, tells us that we're working with a pool of 25 students, all the left-handed students, and we're asking what proportion of those are female. Well, there's 13 students that are female and left-handed. There are 25 left-handed students. So the probability that the randomly chosen student is female, given that the student is left-handed, is 13 out of 25. Similarly, for part 2, if we want to know the probability that a randomly chosen student is right-handed, given that the student is male, we need to restrict ourselves to the category that we're given. So we're given that the student is male, so we know that we're in this row, the male students. And we're asked, if we're choosing just from this pool, in other words, this pool of 59 people, what proportion of those are right-handed? What's the probability the student is right-handed, given that we're just looking at the male category? Well, there are 47 right-handed students in this category, 59 total students, so the probability is 47 divided by 59. There are 21 novels and 18 volumes of poetry on a reading list for a college English course. How many different ways can a student select one novel and one volume of poetry to read during the quarter? This example uses the fundamental counting principle. And the fundamental counting principle says if we're making two choices and we know how many ways there are of making each choice, we multiply those two together to get the number of ways of making the two choices in order. So we're choosing two things. We're choosing a novel and we're choosing a volume of poetry. There are 21 ways to choose a novel, 18 ways to choose a volume of poetry, so the number of ways to select both together is the product of those two, or 378. Notice if we flip things around and made the choice of poetry first and the novel second, it would just be 18 times 21, which is still 378. So the order that we think of the choices doesn't matter. It just matters that we consider that there are two separate choices that we're making, and we have a certain number of ways of making each choice. Assume you work at a pizza parlor and you're offering a special on large two-topping pizzas. Your toppings are broken into two categories, meat and veggies. The toppings must be chosen with one from each category. In other words, they have to choose A meat and A veggie. How many different two-topping pizzas can you make under this restriction? So again, we're making two choices in order. We're choosing the meat to put on the pizza and the veggie to put on the pizza. If we multiply the two together, we'll have the total number of ways of making these two choices. And that's just the fundamental counting principle. So there are 4 options for meat, 3 options for veggies. Multiplying the two together, we get 12 total options for how you could make this two-topping pizza using this restriction. An apartment complex offers apartments with 4 different options designated by 4 categories. So you have the number of bedrooms, the number of bathrooms, which floor the apartment is on, and which view you get. And we want to know how many apartment options are available. In this case, essentially we're making 4 choices: the number of bedrooms, the number of bathrooms, which floor we're on, and which view we get. The fundamental counting principle, again, says that if we can figure out how many ways there are to make each choice, the number of ways of making all these choices together is simply the product of these numbers. So there are 3 ways to choose how many bedrooms to have, 2 ways to choose how many bathrooms to have, 2 floors to choose from, and 3 views to choose from. So multiplying all these together, we get 36 total options for what kind of apartment you could select. You've been given the job of scheduling the movies for the FCC Movie Marathon. You have 4 choices for movies: an action movie, a comedy movie, a drama, and a horror. Luckily for you, you know the fundamental counting principle. How many ways are there to order these 4 movies? So we're going to watch these 4 movies, but we can pick the order we want to put them in. So we have 4 choices to make: which movie goes first, which movie goes second, which one goes third, and which one goes fourth. So we start with the first one. How many movies do we have to pick from to be the first choice? Well, there are 4 movies, so we can put any one of those 4 in the first slot. However, once we've done that, the first slot is taken. Now, for the second slot, there are only 3 movies left to choose from, because we've already used up 1 on the first slot. So there are 3 ways to pick the second movie. Similarly, for the third slot, we've already placed the first and second ones, so there's only 2 movies left to choose from. And then for the last slot, there's only 1 movie left to choose from, because all the others have been placed. So if we multiply these 4 together, 4 times 3 times 2 times 1 is 24. So there are 24 total possible ways that you could order these movies. And now we know that that's called 4 factorial. 4 times 3 times 2 times 1. Anytime we're ordering a certain number of things in the same number of slots, we can use a factorial to calculate that. So organizing 4 things in 4 slots is 4 factorial. organizing 10 things in 10 slots, there are 10 factorial ways of doing that. You have 18 CDs, and you need to arrange 8 of your favorites on the shelf near your stereo. How many ways can you arrange these CDs, assuming that their order makes a difference to you? There are 2 ways to do this problem, and I'll illustrate both. The first is to say, well, I have 8 slots to fill with these CDs. I have 18 CDs to choose from. The first slot, I can put any one of those 18 there. The second slot, I only have 17 left because one of them is in the first slot. And then I have 16 options for the next spot, 15 for the next, and then 14, 13, 12, and 11. And you can multiply all these numbers together to find out how many ways there are to arrange 8 of these 18 CDs in order. If you multiply these together, you'll get 1,764,332,560 possibilities. The other way to do this is to use the formula. Now, since in this case order matters, we'll use the permutation formula, where n is 18, because that's the number we're choosing from, r is 8, that's the number that we select from that pool and then organize. So that would be 18 factorial divided by 18 minus 8 and minus r factorial, or 18 factorial divided by 10 factorial. And if you pull up the calculator and type in 18 and then go to the math menu, scroll over to the probability menu and down to number 4 for the factorial, and then divide that by 10 factorial, go over to the math, over to probability, number 4, we get the same answer, 1,764,322,560. The other way to do this is to use the built-in function for permutations. Notice number 2 on the probability menu is NPR. First we have to enter n, the number that we're choosing from, which is 18. We have 18 CDs to select from. Then we go math, over to the probability menu, select NPR, and then put in r, the number that we actually select, and order. Enter, we get the exact same answer. So really 2 ways of doing this. One, you can think about the slots that we have to fill and how many options we have for each one, and have this descending product that goes from 18 down to 11 and then stops because we run out of slots. Or you can think of the problem as a permutation problem and use either the formula or the built-in function in the calculator. Any way you do it though, you get the same answer as long as you do it correctly. And any one of those methods is fine. The math club has 18 members. According to the bylaws, they need to have a president, a vice president, and a secretary. And we want to know how many different ways can these positions be filled. So again, we have 3 positions to fill, the president, the vice president, and the secretary, and there are 18 people to choose from. That means there are 18 options for who can be president. Once there's a president, though, there are only 17 people left to choose from for the vice president, and then 16 people left to choose from for the secretary. If we multiply these options together using the fundamental counting principle, we get 4,896 possibilities for how many ways we could fill these 3 positions. The other way to do this problem is to think of it as a permutation problem. Since order matters when we select these people, because when we select them, we then organize them into one of these positions, we think of this as a permutations problem, and so we use the permutation formula, where n is 18, that we're choosing from 18 people, and r is 3. We select 3 people and organize them into one of these categories. So we get n factorial divided by n minus r factorial. So if we go to the calculator and type in 18 factorial divided by 15 factorial, we get the same answer we found in the first part. And of course, if we use the built-in permutation formula, we'll get the same thing as well. 18, go to the math, probability menu, select NPR 3, because we're selecting 3 and organizing them, and we get the same exact answer. So again, multiple ways to do this problem, but the fundamental counting principle is probably the simplest to understand. A group of 4 students is to be chosen from a 35-member class to represent this class on the student council. How many ways can this be done? Since there's no mention of order, no mention of position within this committee, we're just selecting 4 students and want to know how many ways can we select them, this is a combinations problem. So we're going to use the combinations formula. Remember, the combinations formula in general is n factorial over n minus r factorial times r factorial. And either you can keep this formula handy or use the built-in function in the calculator. I'll illustrate both for the purposes of this example. So, in this case, n, or the number that we're choosing from, is 35, and r, or the number we're choosing, is 4. So we choose 4 students from this group of 35. So, n factorial is 35 factorial. N minus r is 35 minus 4, or 31, and r is 4. So, going to the calculator, we type in 35, find the math probability menu, select number 4 for the factorial, divided by, and then I want to divide by the product of 31 factorial and 4 factorial. 31 math probability menu factorial times 4 factorial. And we get 52,360 ways to select this group of 4 students. The other way, of course, is to use the built-in combinations formula. So we type in n, 35, go to the math probability menu, and number 3 is NCR for combinations. So we type in n, then select NCR, and then type in whatever r is. In this case, it's 4, and we'll get the exact same answer, 52,360. So there are 52,360 ways to choose 4 items from a pool of 35 items. How many different ways can Harry Potter choose 3 players to be chasers from a choice of 10 players? Since there's no mention of order within these 3 players that are chosen, it's just which players do we select. This is a combination formula. So we're looking for 10C3. N is 10, that's the number we're choosing from, and R is 3. We're choosing 3 out of these 10. So I'm just going to use the built-in function in the calculator. So I type in N, then go to math, probability, down to NCR, 3, and find that the answer is 120. So there are 120 total ways that these 3 people can be chosen from a pool of 10. How many different ways can a director select 4 actors from a group of 20 actors to attend a workshop on performing in rock musicals? Again, no mention of order, so all we're worried about is how many ways are there to pick 4 people? How many different combinations of 4 people are there out of a pool of 20? Again, I'll just use the built-in function on the calculator. So I type in n, go to the math probability menu, select number 3, NCR, 4, and there are 4,845 ways to select 4 people from a group of 20. The Bic Pen Company makes pens in 4 colors, blue, black, red, and green, with 3 tip styles, extra fine, fine, or medium. What is the probability of picking 1 pen at random and having it be a black pen? So now we're going to illustrate doing probability using counting methods. So, again, a probability is the number of ways to get a black pen divided by the total number of possibilities. Well, how many different pens are there? If we're selecting a color and a tip style, there are 4 options for the color, 3 options for the tip, so there are 12 total options. So that's the denominator, that's the number of possibilities. There are 12 possible options. 3 of those are black. You can have black extra fine, black fine, or black medium. So there are 3 ways to get a black pen, and there are 12 total possibilities. Therefore, the probability that our randomly selected pen is black is 3 out of 12. Now, of course, we could also say, well, it's 1/4 because there are 4 colors, and each one of these colors is equally likely. But the reason we did it the way that we did was just to illustrate a simple example of how the fundamental counting principle can be used to count up the number of possibilities in order to do a probability problem. In a certain state's lottery, 48 balls numbered 1 through 48 are placed in a machine, and 6 of them are drawn at random. So we get 6 distinct numbers, there's no repetition. If the 6 numbers drawn match the numbers that a player had chosen, the player wins $1 million. In this lottery, the order that the numbers are drawn in doesn't matter. It just matters which numbers you get. We want to compute the probability that you win the $1 million prize if you purchase one lottery ticket. So, the fact that the order doesn't matter is significant. That means that this is a combination problem. What we're looking for is the number of ways that you could draw 6 different numbers from 1 through 48. So, the number of ways that we can select out of 48 numbers and select 6 of them using combinations. If we use the calculator, 48 is n. Go to the Math Probability menu, select NCR 6. There are 12,271,512 ways that you can select 6 numbers out of these 48 numbers. That's the number of total possibilities for what could come up when these 6 numbers are drawn. Only one of them is the winning combination, though. So the probability of winning is the number of ways to get the winning ticket, there's only one, divided by the total number of possibilities for what ticket you could buy, and that's the 12,271,512. So it's a tiny probability, and in decimal form, it's 0 point and then 7 zeros, followed by an 8. So the tiny chance of winning given the number of possibilities that can occur. If you select a 4-digit PIN, what is the probability that there are no repeated digits? Let's start by counting the number of ways that anything could happen, the number of total possibilities for what PIN you could select. Well, if there's 4 digits, essentially you're making 4 choices. What number goes into each digit? So we have the options of 1 through 9, which is 9 options, or a 0. So there are 10 options for each position. Therefore, multiplying them together, we get 10,000 total possibilities for what PIN you could select. There are 10,000 ways to select a PIN. Now, the second part is a little trickier. To calculate the probability that there are no repeated digits, we need to count the number of ways that you could select a PIN without repeating digits. Once we count the number of ways of doing that, if we divide that by these 10,000 total possibilities, we'll have the probability. So, counting the number of ways to build a 4-digit PIN without repeating any digits. It turns out that this is equivalent to choosing 4 digits out of the 10, right? The 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, and we select 4 of them without repetition. So you can think of having a bag with the numbers 0 through 9, and you pick out 4 of them, not allowing any repetition. And you want to know how many ways could I do this. So that's why it's a combination problem. And that's the tricky part of this problem, is recognizing that that is how to solve it. That we're selecting 4 of these numbers out of the numbers 0 and then 1 through 9. But once we see that, calculating is pretty straightforward. We'll use the calculator again and the built-in combination function. So 10 Math Probability NCR 4. There are 210 possibilities for how you could build a PIN without repeating digits. So the probability that that happens randomly is the number of ways that can happen divided by the total number of possibilities for what can happen. 210 divided by 10,000, which as a decimal is 0.021. So about a 2% chance that no digits repeat. Assume that you're still in charge of planning the FCC movie marathon. Remember, we have 4 types of movies: action, comedy, drama, and horror. Assume somebody also brought a thriller, so now we have 5 types of movies total. In order to find out the order of the movies, you decide to throw all the names in a hat and plan to draw one name out of the hat at a time, and the order will be determined by how they're pulled out of the hat. What we want to know is, what is the probability that the thriller is played 4th and the horror movie is played 5th? Again, anytime we calculate a probability, it's simply the number of ways that our event could happen divided by the number of total ways that this scenario could play out. So we need to count up the number of ways that this precisely could happen. The thriller is played 4th and the horror movie is played 5th. And divide that by the number of ways that anything could happen, the number of total possibilities for for how these movies could be ordered. So let's start with the numerator. Let's start with counting how many ways could the thriller be played fourth and the horror movie be played fifth. If we use the fundamental counting principle, we think about, well, there's 5 slots to be filled, 5 movies that we're ordering. In the first slot, we have 3 options, because there are 5 options total, but if the thriller is going to be played fourth and the horror movie is going to be played fifth, then those 2 are not possibilities for the first one. So there are 3 possibilities, the other 3 movies. Then there are 2 movies that aren't the thriller or the horror that can go in the second slot, and then 1 movie that can go in the third slot. And then the thriller goes in the fourth slot, and the horror movie goes in the fifth slot. You can also fill in these slots by filling in the fourth slot and the fifth slot first with 1s, and then recognizing that there are 3 movies left to go into the remaining 3 slots. In any case, this tells us that there are 6 ways that the thriller could be played fourth and the horror movie could be played fifth. The other way to do this is to use permutations. And the way to do that is to notice that if the thriller is fourth and the horror is fifth, the number of ways that that could happen is just the number of ways that we could order the first 3 movies. So there are 3 slots that we still have to fill, 3 movies to fill them, so 3p3, permutations where n is 3 and r is 3. And of course that turns out to be exactly 6 as well. Then the denominator, or the number of ways that we could order these movies in total without this restriction, again we can use the fundamental counting principle. There are 5 movies that can go in the first slot, 4 in the second slot, 3 in the third slot, and then 2 and then 1. And 5 times 4 times 3 times 2 times 1 is 120. So there are 120 total possibilities. That too we could do as a permutation problem, where we have 5 slots to fill, 5 movies to choose from, and we're organizing them, so it's a permutation problem where n and r are both 5. Again, if we use the calculator for that, we get 120. But it turns out that these permutation problems can all be done with the fundamental counting principle, so I've shown that here. Then, of course, the probability that this scenario happens is the number of ways that the scenario happens divided by the total number of possibilities. So if we divide 6 by 120, that's the probability. And of course we can simplify that fraction down to 1 over 20, or write it as a decimal, which is 0.05. So there's a 5% chance that if we randomly organize the movies, the thriller will end up in the 4th slot and the horror movie will end up in the 5th slot.